Hi everyone, this is Dr. Untam. In this video, I'm going to explain how to apply Kirchhoff's rules to solve DC circuits. So why are Kirchhoff's rules important? One may ask. Well, it turns out that there are many ways in which resistors could be wired so that it's impossible to reduce the circuit to a single resistor using the series or parallel combination formula. For this kind of circuit, Kirchhoff's rules provides an alternative solution. The first rule is called the Junction Rule, and it states that the sum of currents at any junction must equal to 0. Alternatively, it could be stated as the sum of currents into a junction must equal the sum of currents leaving the junction. The first rule is a statement of conservation of charge, and the equation for the first rule is shown here. An alternate equation would be sum of currents going in equal to sum of current going out. So this way, currents going in are treated as positive and currents going out negative. In this figure, I1 represents current going into the junction, and I2 and I3 represent current going out. Therefore, Kirchhoff's rule for this junction is I1 equals I2 plus I3, or I1 minus I2 minus I3 equals 0. Again, this is required by the conservation of charge. The diagram B shows a mechanical analogy of the first rule. So the first arrow on the left shows water flowing into a pipe that has two outlets. The sum of water flowing out of the branches must equal the amount flowing into the left pipe. Again, this is required by the fact that water cannot be created or destroyed inside the pipe. Another example that we see every day is that of traffic. So if we let this junction represent a road junction, so the amount of traffic flowing into this junction must equal the sum of the traffic going out of the two outlets. Now, the loop rule states that the sum of potential differences across all elements around any closed circuit loop must be 0. It is a statement of conservation of energy, and the equation for the loop rule is shown here. This figure again illustrates the application of the loop and junction rule. So the figure A shows the current in, which is I1, the current out, I1, I2 and I3. Therefore, I1 equals I2 plus I3. Figure B shows an example of a circuit with 4 circuit elements. These elements could be resistors. So, in going around the circuit in the direction of the arrow, which represents the loop, one traverses these 4 elements. Therefore, the sum of the potential differences V1, V2, V3, and V4 must equal 0. So more about the loop rule. It's very important to note that in applying the loop rule, there is a sign convention that must be observed. So in A, as we travel around the loop, crossing the resistor from A to B, one goes in the direction of the current. And knowing that current flows in the direction of high to low potential, there is a decrease in potential as one traverses the resistor from A to B. Therefore, the potential difference is minus I times R. In B, the resistor is traversed in the direction opposite to the current. Again, we're going from A to B. So now we're going from low to high. Therefore, we go in the direction of increasing potential. So the potential difference across the resistor in figure B is plus I times R. So a simple way of remembering this is that when traversing a resistor in the same direction as the current, then the potential difference is minus I times R. And when traversing the resistor in a direction opposite to the current, the potential difference is plus I times R. Now for EMF sources, when an EMF source is traversed from A to B, such that we're going from low potential to high potential, that's the negative terminal to the positive terminal, we go in the direction of increasing potential. Therefore, the potential difference across the EMF source is plus E, where E is the EMF of the battery. In figure D, the source of the EMF is traversed in the direction from high to low, positive to negative. Therefore, we're going in the direction of decreasing potential, and the potential difference is minus E. So this is a simple example of the loop law for a circuit that has just one EMF source and one resistor. So as we go around the circuit in the direction of the purple loop, one traverses the resistor in the same direction as the current. Therefore, the potential difference across the resistor is minus I times R. And one traverses the battery from low to high, direction of increasing potential. Therefore, the potential difference is plus E. So you can pause this video and write down these notes on the application of Kirchhoff's rules. Okay, so here is a more problem-solving strategy. Okay, more problem-solving strategies. And after solving the problem, you need to check your numerical answers for consistency. And if any current value is negative, it simply means you guessed the direction of that current incorrectly. Okay, so in the next video, we're going to look at this example, and we're going to write down the equations for Kirchhoff's first rule at the two junctions, and then we're going to see how to apply the loop rule to this same circuit.